beautiful institute here at the Canary Islands. So I'm going to speak on the origin and evolution of halo stars and globular clusters, basically taking from the R Process Alliance. So as David mentioned, I'm a postdoc at the University of Florida and is mainly interested in tracing the galactic archaeology. So what is galactic archaeology? Like we know in our current life, archaeologists dig deep into the ground to discover artifacts or signatures of lost civilizations, lost things. We, as galactic archaeologists, we dig deeper, but deeper in space. Not deeper, right, in distances. We can dig deeper, we can go to large distances, watch objects at larger redshifts, get the photon photon deprived signals, very poor signals. Instead, we try to go back in time. We try to find stars that were formed very early in the galaxy, very early in the universe. There are low mass stars which are still shining today in the outskirts of our galaxy. So we try to find this ancient stellar population that's been there all the time in the universe, and that allows us to get a good signal using a moderate sized telescope. So in this field of stellar archaeology, there are several aspects to it. There are theoretical aspects, there are simulations, there are observations, and then there are nuclear experiments. So we, as observational astrophysicists, we do the observations. We try to look at stars, derive the abundances of individual elements that we find in the periodic table, pass on the information to the theoretical scientists. They also obtain informations from the nuclear experiments, and they combine all of this to form a theory of the galaxy, how the galaxy formed, how the galaxy evolved, and chalk the chemical history, the chemical evolution of a Milky Way galaxy. This, in a nutshell, is called galactic archaeology. And this is like a web that you can see. All these small fields are intertwined with each other to give us a complete picture of what's going on out there. To talk about the hierarchical galaxy formation model, the fast stars and the first mini halo were formed a few million years after the Big Bang, and they are massive stars. They exploded as the first supernovae. These supernovae explosions enriched the ISM, and the first mini halos, they combined to form the protogalaxy, and these protogalaxies combined to form the current galaxy of the Milky Way. So these accretion events of several smaller subhalos of galaxies into the current galaxy is called the bottom-up approach, and that forms the current Milky Way. So this hierarchical galaxy formation model talks about smaller substructures formed earlier, and they merged and combined to form larger structures. The dark matter halo of the Milky Way still today contains a large number of subhalos. And these structures, this merging of smaller structures into the bigger galaxy is still ongoing. And there are signatures of tidal tails, of structures that are forming, accreting into the galaxy. These are several examples of such streams that are still visible if we point our telescopes, use some technology to find over densities of objects in the sky. They tell us about the kinematic and chemical properties of these structures that are merging within the galaxy. Coming back to a problem, so we as galactic archaeologists, we try to explore the earliest times. What was there in the infancy of the galaxy, infant days of the universe? So after Big Bang, it was hydrogen and helium and traces of lithium. At this point, the population 3, or the first stars, were formed, and they exploded as massive stars, as massive supernovae. And these supernovae ejected heavier metals. Heavier metals are metals heavier than lithium, or metals heavier than helium. So all these metals are synthesized in stellar interiors, in explosion events, as well as during the lifetimes of the star. And ejection of the first supernovae enriched the pristine ISM for the first time. So when the subsequent stars were formed, they had slightly higher content of heavier elements. This process went on and on for several generations, and now culminated in the sun. Sun is a lot metal rich compared to the first stars. Metal rich implies having more content of heavier metals than the first generation stars. So we try to find stars that have the minimal amount of heavier elements. So the less the heavier elements in a star, the earlier it's likely to be formed. This is the principle that we adopt to look at stars and understand whether these are formed early or later in the universe. And we try to understand the nucleosynthesis and chemical ills from the first early supernovae to chalk what were the astrophysical conditions of the universe when these stars were formed from their birth clouds. Looking at all the elements that we can measure sitting on Earth based on whatever data or signal we get, we find the periodic table. And this table shows you each element and what are their potential sources in the universe. For example, there can be Big Bang nucleosynthesis that forms hydrogen and helium, traces of lithium and beryllium. There are other events like merging neutron stars that forms the heaviest of the elements. There are processes in the stellar interiors that forms odd Z elements, alpha elements. There are processes in supernovae that forms a certain fraction of elements. So there are nuclear experiments as well that tell us about the cross section and other information. So we combine our observations, measurements in the stars of these elements, try to compare with the yields from the experiments, and try to understand what could be the temperature, pressure, and conditions at which these elements could be synthesized in the stars that tell us what are the sites and origin of these elements. In this study, we focus on the heavier elements. There are several sources for the light elements as well, but the discrepancy is larger as we go in elements heavier than iron. So elements up to iron can be synthesized in stellar interiors. Beyond that, elements can be synthesized only via neutron capture process, elements heavier than iron. And this can occur in two ways, slow neutron capture and rapid neutron capture. Slow neutron capture is known to be produced only in AGB stars, both intermediate, massive, and low mass AGB stars, whereas the rapid neutron capture has put us in a dilemma. It could be neutron star mergers, it could be several other things as well. So the proposed sites for our process nucleosynthesis are neutron star mergers and core collapse supernovae. The core collapse supernovae explain the early formation of these R process rich stars. So the stars we find R process are also very metal poor. So they form very early in the universe. The question is, can neutron star mergers come into effect so early in the universe? The answer that we know now is we don't know, because the fit we see here for neutron star merger, it tells us that there is a delay. There is a delay when neutron star mergers come to dominate the population, but we find stars that are enriched in our process before neutron stars come into play. So the other potential site is core collapse supernovae, and core collapse supernovae fits the data perfectly. However, there was a gravitational wave discovery back in 2017, and that was resulting from a binary neutron star merger, and we could conclusively find evidence of strontium in the signal from this gravitational wave. And that tells us that our process is definitely happening in neutron star mergers. So yes, neutron star mergers is definitely a candidate for our process, but core collapse supernovae, it fits the early distribution, but we do not have any evidence of it producing our process nucleosynthesis. On the contrary, theoretical simulations tell us they are unlikely to produce our process except in certain very small classification of these core collapse supernovae. The additional sites for our process include several, just to name a few: neutron star mergers, massive stars, black hole neutron star mergers, magneto-rotational supernovae, collapsers, and black hole accretion disk. And it's not just one of these, it could be all of these combined in some way or the other, like different layers of contributions entangled with each other. And it's extremely difficult to separate what are the actual sources of this pollution in the stars. So our process abundances, why are they so important? So if we look at the mutual abundances of these R process elements that are heavier than iron, they show a distinct pattern. This distinct pattern is found in the oldest star that you can see in the universe. It's found in the sun as well, and it's exactly the same pattern. So there must be something unique. There must be something very strong that affected the entire gas and the very early epoch that puts up this stamp or signature of this pattern in all sort of stars and populations that we can find. And the discrepancies come up later with when we find more number of stars. The discrepancy comes here. The dispersion for the lighter R process tends to be very large. And that leads us to assumption that there can be more than one sites or sources for R process. There can be dispersion at the heaviest end for thorium, uranium, and that tells us there can be yet another sources for R process. So there could be different sources of R process that is contributing to different parts of the spectra, but at the same time, they all are producing a very robust, a very universal R process pattern for the main R process. So this is called the main R process, the lanthanides group. This is the like lighter R process or limited R process, and this is the heavier R process. The other proposed site is, could R process be produced in supernovae? That will lead us to a very strong solution that makes all happy, but unfortunately, theoretical predictions tell us that that is very unlikely. Coming to the R process alliance, so this is a group of people who are very interested to solve this problem of R process. How are they formed and where are they formed? And these are the first early results from the R process alliance till 2019. And you can see how the number of stars are drastically increased with the onset of the R process collaboration starting 2013. So in this study that I'm mainly going to talk about, metal poor stars and their follow-up observations using GTC. So this led to the R process alliance data release 5. And this is the distribution in V magnitudes. We look at the faintest population of the R process alliance with magnitudes fainter than 13 in V. And these are observed through Horus. And Horus was the ideal instrument to observe this because all these stars are very faint. And Mike, the usual spectrograph we observe R process alliance is Mike, but Mike doesn't allow to go beyond 13.5 or stretch it to 14 with longer exposures. So we employed the tool spectroscopy made harder, and the data was reduced using the pipeline developed by Carlos or chain. And this is the observational details of all the target stars with the information. And these are some examples of spectral synthesis. The carbon molecular G band for 2 of the stars in this sample. And this is the analysis for the neutron capture elements. So always red denotes the best fit, and the deviations for plus and minus 0.5 text is shown. And the black line over here corresponds to complete absence of that particular element. So this is the technique we employ to derive the abundance of each element in a given star that we observe. And coming to the abundance trains. So these are the abundance trains for the alpha elements. So in the halo, we expect the stars to be enhanced in alpha. So magnesium, silicon, calcium, and titanium. The titanium is a proxy for alpha. It's not exactly an alpha element, but it behaves as an alpha element. So we all find that they are enhanced in the alpha elements, and the different classifications of R1, R2. So, okay, I missed this point. So R1 stars are the R process enhanced stars that are moderately enhanced in R process. And R2 stars, such stars which are strongly enhanced in R process. So there are classifications of these two. And there in this study, we also find certain magnesium poor and globular cluster stars. Looking at the yields for the iron peak elements, they all usually follow they're very strongly following the trends for iron, with exceptions with a stronger dispersion for vanadium and cobalt. Manganese is usually subsolar, but you also note that there are strong non-LT corrections that has to be included on these stars to compare them with the theoretical yields for the production ratios of these elements. Continuing abundance trends for carbon. So the dotted lines here show the blue line. So any star above this line are called carbon enhanced metal poor stars. And their origin is also a matter of discrepancy, which we shall talk about a bit later. And these all are subsolar carbons. The expected carbon is between these two lines. Similarly, odd Z elements, they show the odd-even pattern, and they are often used to understand what was the mass range of the original supernovae that could have contributed to the formation of these stars. Similarly, we find the neutron capture elements. So as I was mentioning, so any star above this line here, that's called R2 star. And any star within this here is called an R1 star. These are not arbitrary. There are certain definitions and reasons that led to uh, this postulate of defining them in different categories. And these are all stars that are not enriched in our process. And finally, fortunately, we had a star in common with several other studies done in 2018 by Therese Hansen and Charlie Sakari. And we compare our estimates from Horus, from their data in Mike, and within abundance dispersion, they show remarkable consistency. So coming to the alpha elements. So alpha elements is mainly produced in core collapse supernovae for metal poor stars or at the metal poor regime. We separate the alpha elements into two groups, the hydrostatic alpha elements, which are comprised of calcium, silicon, titanium, and the explosive alpha elements, that's magnesium and oxygen. So we measure the difference between these two groups of alpha elements to understand their mutual contribution and plot it as a function of magnesium over Fe. We find they fall along a trend, and as expected, the most metal poor sample, the most metal rich samples shown in blue here, they're all color coded by metallicity, fall at very low magnesium. So this is mainly coming from like type 1 supernovae, and these are all products of core collapse supernovae. We plot the yields for a 15 solar mass and 25 solar mass core collapse supernovae of zero metallicity and metallicity dependent integrated functions of hypernovae and supernovae combined are plotted in colored boxes, colored as per the metallicity. And we find that all the contributions from core collapse supernovae and hypernovae contributes to this chunk of elements at the bottom of the plot. So depending on the nature of the deviation, if the deviation between these two groups of alpha elements is more than 0.2, they're likely to be contributed more by type 1 supernovae. And if the deviation is less than minus 0.2, the primary progenitor is likely to be type 2 supernovae with or without contributions from hypernovae. We look at magnesium as an indicator of alpha element coming from core collapse supernovae, and we look at europium, which is a primarily a R process element. We look at the magnesium over europium to compare the relative contribution of core collapse supernovae versus contributions from R process as a function of metallicity. We see that trends are decreasing for both R1, shown in green, and R2, shown in purple. So they follow a similar pattern, but the spread of R2 stars is much higher than R1 star. And red here are all the stars that are not enhanced in R process. So the stars and gray dots here are taken from Roderer et al. 2014, which includes all the non-R process enhanced stars. Following the histogram, they also pick at different values of magnesium over europium. So R1 stars pick at a higher magnesium over europium compared to R2 stars. This primarily stems from the definition of how R1 and R2 stars are defined. But the point to note, the interesting point to note is they have a decreasing trend with metallicity. The reason for this decreasing trend with metallicity could be contributions from type 1a supernovae, but that comes at relatively higher metallicity. So the dominant factor at this metallicity regime needs to be looked into further. Now we look at light and heavy R process nucleosynthesis. So as I mentioned earlier, strontium, yttrium, zirconium are the lighter R process elements, whereas europium, barium, and the group of lanthanides are the heavier R process element. So we take strontium as a yardstick for the light R process and barium as a heavier R process. So when you look at the smaller, when you look at the smaller, less massive and more massive subhalo, the products of neutron star mergers are likely to be diluted in a larger subhalo, whereas they tend to be more dominant at a smaller subhalo. And supernovae is known to produce, it has the energy to produce only the lighter R process element. At least that's what we understand right now. For the heavier R process element, it has to be more energetic events like collapsers or neutron star mergers. So a strontium over barium, lighter over heavier, greater than 0, and lighter over heavier, less than 0, will have different origins. And if you look at this figure here, so strontium and barium rises at different rates compared as a function of magnesium for the same set of stars that we observed. So this tells us that strontium and barium are not synthesized in exactly the same site. We look at this further. We take strontium over barium and plot it as a function of magnesium over H for all R1, R2, and non-RPE stars. And we find that for magnesium over hydrogen higher than minus 2.5, this shows a downward trend. So as magnesium over H increases, strontium over barium decreases. That is, with increase in magnesium, there is relative decrease in strontium. So if strontium, the lighter R process elements, are produced in the same site as magnesium, they should show a correlation, which they don't. Rather, they show an anti-correlations, which tells us that strontium is not conclusively produced in supernovae type 2, or lighter R process elements may not, or supernovae type 2 may not be the only progenitor for lighter R process elements as we often associate nowadays. Okay, finally, we plot strontium and barium, sum of strontium and barium as a function of europium over H. We take the theoretical L's from Erika Hombeek, is the black line that shows the L's, expected L's from neutron star mergers. The purple are the R2 stars and green are the R1 stars. And you see purple falls very close to the theoretical L's for neutron star mergers, whereas green shows a larger deviation. And this deviation increases with increase in europium. This tells two things. One, R2 stars are probably the closest progenitor, R2 stars are probably the closest thing that we can find that has an origin in neutron star mergers. R1 stars, the stars that are moderately enhanced in our process, can have several contributions other than neutron star mergers. We did also find a star that is bright, and we can find thorium. This is a result from the HESP-GOMPA survey. This was observed in HESP, the spectrograph, the 2-meter class telescope in India, and it's a resolution of 30,000. These are the spectral synthesis for these elements, and this shows the R process pattern. And so discovery or detection of thorium allows us to measure cosmochronometric age. So we take the initial ratios for these elements as they decay with time and find how much time the star must have elapsed to produce the current observed ratios of these elements. And this thorium-rich star also falls right on the edge of the accreted stars. This is the locus of the Nissen and Schuster data. And this star falls right on the edge. And here they also shows the position very close to the accreted zone. And these are the kinematics. But from the kinematics, we cannot really determine whether these are accreted or they are in situ population. So this star is again taken up for follow-up in the RPA and is currently undergoing an analysis based on higher resolution and higher exposure times. We also find certain globular cluster stars in the halo. So globular clusters show certain anticorrelations for lighter elements that are not found in halo stars. For example, they're enhanced in aluminum, they're enhanced in sodium, they're depleted in carbon, they're depleted in oxygen, and they're depleted in magnesium. So this enhanced aluminum, enhanced sodium, enhanced nitrogen feature is often associated with finding stars that were originally born in globular clusters. We find a similar star here that could be globular cluster escapee, but it has a much lower metallicity. It has a metallicity of -3, whereas the known metallicity floor for globular clusters is minus 2.5. So you don't expect globular cluster stars to go this low in metallicity, but there are also other studies that find certain of these objects. And if we look at this star versus all the prominent globular clusters, the bona fide globular clusters from literature, this star falls within the parameter space defined by other globular clusters. We also look at the origin of carbon-enhanced metal-poor stars. They could have different origins, like mixing and fallback supernovae, faint supernovae. So this is a paradigm defined by Jean-Mi Yoon and Tim Beers back in 2016. And they defined CMP no and CMP S and group 3 stars to be of different progenitors. So the stars we find here are CMP no. What is CMP no? CMP no are carbon-enhanced metal-poor stars with no elevations in neutron-capture elements. So except one, all our stars are CMP no. And these CMP no stars are very important because as we go to the early universe, the more we go to the metal-poor end, the more is the number of CMP no stars. And CMP no stars absolutely dominate the populations at metallicity lower than -4. So looking at the distribution, all the stars we find in this study are CMP no stars. And again, they are taken for follow-up studies with a Pepsi spectrograph in the US. And we're expecting some good results based on the origin, the CNO cycling, and other products from these stars. And they are the trends with lighter elements because you see group 2 and group 3 stars scales differently with absolute abundance of carbon as well as metallicity. So we put our stars on the Jean-Mi Yoon's data to look at whether they actually follow the trends, even for the lighter elements, apart from iron and carbon, which they do. So that brings us to a summary of this project. So we look at the different neutron capture elements, the alpha elements, the iron peak elements. We look at the population differences. We take insights from the correlations, anti-correlations, discrepancies, and difference between the two. And we also look at the astrophysical implications at what could be the R process progenitor, what could not be the R process progenitor, and what could be different than what we expect from such studies. So that is the first. David, how are we doing on time? 15 more minutes? Cool. So that allows me to go to my second project, which is probing abundance variations in multiple populations of metal-poor globular cluster, NGC 2298, using Gemini South. So NGC 2298 is a very low mass metal-poor globular cluster, and it's among the lowest mass globular clusters in the halo. So this is a picture of NGC 2298. This is taken from, I think this is taken from the NASA, and this is taken from the skylive.com. And this is what it looks like in the sky. And if you want to look at NGC 2298, this is the signature that you should follow. So NGC 2298 has several photometric follow-up studies that shows it has multiple generations based on the photometric lines. But there is lacking a deep spectroscopic study of this cluster and to understand how this cluster might have evolved. Why are globular clusters important? Globular clusters are among the structures that were formed very, very early in the universe. And these clusters are still there and they retain their gas. The potential of the globular clusters don't allow gas to escape from them, except for certain events like evaporation and slow accretion into the galactic disk. So if we find these globular cluster stars, they all retain the primordial signatures of early nucleosynthesis in the galaxy. So the first task to carry out this project was target selection. So we take the catalog from Vassiliev 2021 and we project the bona fide globular cluster members into the sky. Fortunately, they gave us a probability of a star belonging to this particular cluster. And we put the cutoff at 99.5%. So the stars we see in black are all stars from the Vassiliev catalog pertaining to NGC 2298 that have a probability of cluster membership greater than 99.5. We then take the proper motions along RA and DEC, and the blue are the sample that we choose based on the proper motion space, and After doing the proper motions, we also look at the parallax, and we take stars that are only within 3 sigma of the parallax of the cluster. So 3 cuts. One is the Vasiliev catalog probability. The next is the proper motions along area and deck. And third is the parallax. On doing this, we find the blue and black. So blue are the selected targets, and black are all the targets from Vasiliev with probability greater than 99.5. Finally, for feasibility of the study, with GHOST. So GHOST is the newly commissioned spectrograph in Gemini South. And for feasibility with GHOST, we needed stars that are brighter than 16.0 in G. So we take the brightest of these candidates in red to do the study. Looking at the CMD, this looks like this is the CMD that we find after doing the stellar parameter, after finding the stellar parameters based on the data, the log G temperature, and this is where the stars lie. So they all lie to the tip of the AGB. And the stars could be classified on first generation and second generation. How we do that is I'm coming to a minute, but the age of the isotron overlaid is 11 gigayears. And this is a spectral synthesis. This is for the carbon CH molecular band, the G band at 4313, and this is a CN molecular band. And these are the synthesis for the different neutron capture elements, starting with strontium up to osmium. We could also find upper limits for thorium in some of these stars. So how do we classify stars into first generation and second generations? So the first stars in the globular clusters were very similar to the halo stars we find. So when these stars exploded as supernovae, they had their abundances slightly different. The exploding winds from supernovae are enriched in certain metals. So these enriched winds from supernovae or AGB stars pollute the pristine gas of the globular cluster. And when the second generation stars are formed, they are formed out of this enriched gas. And that's why they retain the signatures of this enriched gas. Why this doesn't happen in the halo? Why don't we find these stars in the halo? The simple reason being, in the halo, the gas dissipates. In globular cluster, it's a bound system. The gas is not allowed to escape. So the gas recycles over and over, forming subsequent generations of stars. When you look at these certain samples from the globular cluster, we find stars that look exactly like the halo. Those are the stars that are formed first, and there are stars that are formed with different abundances. Those are the recycled products that came in subsequent generations. And these signatures include, as I mentioned earlier, elevation in sodium, elevation in aluminum, and depletion in carbon. So the stars, as I define, are enhanced in sodium, depleted in magnesium, are second generation stars shown in blue. Stars enhanced in aluminum, depleted in magnesium, are shown in blue. Also stars, the same stars are also enhanced in nitrogen and depleted in carbon. That shows that all the signatures fall along the same expectations. Like all the second generation stars have these abundances elevated or depleted or different from the first generation stars. So the rest of this presentation, all the second generation stars will be in blue and the first generation stars will be in red. So insights from the alpha and iron peak elements. So ideally, globular clusters in the early days were known to be a single population. They hardly show any deviation. As we look deeper, as we probe into a larger population with better quality data, we do find star-to-star variations. But even at this current era, the star-to-star scatter for iron peak and neutron capture elements are very low. And as we expect, for example, if you look at calcium, all the 14 stars, the dispersion is less than 0.1 dex for calcium for both the generations. The numbers printed here are based on a statistical test, Brown-Forsythe test. It tests for the dispersion between these two populations. So any difference in dispersion, intrinsic dispersion between these two populations are given by a number less than 0.1. Here we find something interesting. Most of the elements show very same distribution, very same dispersion, and very same trends for all the alpha and iron peak elements except scandium, nickel, and zinc. Scandium, the dispersions is really different for these two populations. Similarly, for nickel and zinc, they show significantly different dispersions. For copper, it shows the same thing, the dispersion is very high. So out of all the alpha and iron peak elements, what happened the second generation stars that could produce this anomaly. So there is a time gap between first generation and second generation, formation of the second generation globular cluster. So what events might have occurred? Is it the mixing of the globular clusters that got uniform? Is it a new source, a new site that produced some nucleosynthesis into the gas to produce uniformity? We don't know. But this is what the data tells us. There is difference in 2G and 1G stars for these elements. Continuing with the neutron capture elements, we find a similar difference in dispersion for europium and strontium. Strontium, the difference is really high. For all the 1G stars, the dispersion is limited to less than 0.05 dex, whereas they spread over 0.3 dex for 1G stars. Similarly, for europium, for barium, this difference is not so stark. So there must something have happened between the time when the first generations were formed and the second generations were formed that led to reduction, the dispersion of these elements in that time. On the middle panel, middle row, we eliminate the dependence on metallicity and plot as a function of magnesium over H. And we find the same similar distribution. So definitely the dependence on iron doesn't introduce these dispersions. On the lower panel, we again do the lighter R process over heavier R process as a function of magnesium. And we find that for the first generation stars, which shows an increasing trend with magnesium. So as magnesium increases, strontium increases compared to europium. Similarly, as magnesium increases, barium increases compared to europium. So with increase in barium for the first generation stars, there is increase in magnesium, barium, and strontium simultaneously. But we don't see that again in second generation. Looking at the nucleosynthesis and R process pattern, so this is like a summary of all the elements we find in all these stars. So red, again, is first generation, blue is second generation, and this shows the light element anticorrelations that we find in these clusters. And this shows the uniformity in the alpha and iron peak, except for scandium, zinc, and nickel, cobalt. And then we find, so this is again, we coming back to the same R process pattern. The dispersions for strontium, zirconium is higher. This shows the main R process up to thorium. However, the dispersions for 1G stars again is higher than the 2G stars. And interestingly, the dispersions for the main R process, you see, is significantly higher than the lighter R process. Ideally, we would expect dispersion in the limited R and uniformity, universality in the main R process. But there is a certain distinction here as it shows increased dispersion in the main R process. So to summarize, we observed 14 stars using ghost spectrograph on Gemini South. We could categorize them into first and second generation stars. We looked for star-to-star dispersion and anomalies for all the elements that we could measure. We noted certain differences between light, heavier elements, light and neutron capture elements. We find a universal R process pattern with slightly low abundances for europium and increased dispersion at the main R process end. So there are some exciting results on the way. So the fifth data release of the RPA that I just spoke about in the first project has fortunately been accepted in the Astrophysical Journal supplement yesterday. Should be on archive later this week. Keep an eye for it. And there are results from, interesting results from GHOST that I discussed, Gemini South, Globular Cluster Instituto 298, that hope to submit sometime soon. And currently I'm working with David and Carlos here on the GTC Osiris follow-up of M15, looking for extra-tidal stars of M15 to understand whether it has tidal tails or are stars escaping from these globular clusters and contaminating the halo. So these studies aim to understand nucleosynthesis across different stellar environments, illuminating the early universe formation and evolution. And as it says in the ISC homepage, the history of astronomy is a history of receding horizons. And we are here to look at the horizons in time to see how the entire cosmos has evolved. With that, I thank you for your attention.
Thank you. Thank you so much, Avrajit, Bandyopadhyay. Yeah, we have time for questions. Please raise your hands. Carlos?
Very nice stuff. I, I was intrigued by a plot you showed early on, comparing abundances from a study by Hansen with the ones that you derive for a star in common uh, from the Horus.
Yeah,
It was, I mean, the figure showed
yeah, I remember.
fair agreement.
Yeah,
This one at the bottom, right, on the bottom right.
yeah,
Okay, I mean, one question that I have is about the details, right? Because I mean, there is fair agreement, but there are some differences, and this could be due to many reasons. Is everything the same, but the data is the same model atmospheres involved, the
yeah,
same
yeah.
codes?
The
Uh,
data, the model atmosphere, and the codes, they all are exactly the same.
Only the data
The
change.
data from is for a different telescope.
Okay, then it might be that these differences are large,
Yep.
not as small, right? Because then the scale is large. But if you zoom in,
Yeah,
uh,
but when you look at the spreads or the error bars for their study as well as for our study, it's within the error bars for most of the elements here.
okay, I see. So the error bars are from but if the systematics are the same because the analysis is exactly the same, the lines and the atomic
Yeah,
data is exactly the same, then the error bars shouldn't include systematics. It should only be like the spread, the line to line spread, maybe,
yeah.
or not even that. It will be like the noise
It is primarily the noise.
in the noise.
Noise.
Okay, very good. And I mean, I like the fact that this plot has error bars, and the in the other ones here you have also this error bar indication
Yeah.
that gives you a good hint. But in many of the other plots, it's very hard to judge
For
whether,
the globular clusters plot.
yeah, for example, uh,
Yeah, I haven't put it for the globular cluster because they all are mostly within 0.15 tex. So I probably added in the paper. So it's all like for globular cluster, it's mostly very uniform, the error bars we get from Gemini.
I see, and very small. So
Yeah,
it's basically what we're seeing is the scatter is real.
exactly.
It's start to
Exactly.
start.
For globular clusters at least. Yeah.
Oh, and when you compare strontium and barium abundances, well, you have here some plots. Right, for example, it's a bit difficult to judge whether the difference between R1 and R2 are significant in the sense that
So when I tried to fit this distribution separately for R1 and R2 with a Pearson correlation coefficient. For R2 stars, the coefficient shows a mild trend, whereas for R1, it's a moderate thing. And also we find that R2 stars by this purple circle is limited to this region. Like they all are like very episodic around magnesium minus 2.5. And here you find it's mostly all R1 stars. There is hardly any R1 stars spreading beyond magnesium minus 2. So these are like the, and R2 stars do not really show the trend as clear as R1 star. So these are the like differences we find between these two populations, these two subpopulations rather.
on one final link question is, so in this case, for example, the error bars would be able to account for the width of this band.
Exactly. Yeah.
And what about the outliers? There are a few stars that are like 2 or 3 sigma off, like very high, like the R2 star -2 in in magnesium over hydrogen.
Yeah.
Uh, is that one explainable by the error bars, by the noise? It's
The,
really like
because
text of.
the outliers like here or here or here, they are certainly not explained by the noise because they are far beyond the, even the 2 sigma noise levels. So they, because the art process, like there could be several events that contributed to europium. Magnesium is coming from core collapse supernovae, but europium could have several sources. So here we try to fit the bulk of the stars that we find having europium excess of 0.3, but certainly these outliers are something that we are as clueless as ever. We really don't know what could be the sites or origin of these elements.
Those are very interesting. Thanks.
Thanks.
Questions? Yeah.
Thank you very much for the nice talks, or two talks actually. I have a question to the second part, to the globular cluster. You showed these different like generation 1 and generation 2, or like first generation, second generation, you called them. And you showed the chemical difference very, very nicely. Is there any estimate, maybe you mentioned it and I didn't see it, are there estimations that the ages of those stars, are there age estimations that you see, okay, there's a difference between the one generation and the other, or is this not expected at all?
No, the age expectations are not likely to be very significant. There is no way we can measure the age to that precision,
Yeah.
because there is one first generation, and there are all subsequent generations are unitedly called as second generations. So they can be like orders of 10 to the power 6 years. So it's very difficult to understand. There was a paper by Ivan Kirby last year that did find this they calculated the crossing over time and tried to correlate that with first and second generations. But again, that is more of a rough estimate, not something very precise that you could go by.
Theoretically, there must be a difference, but it's not really
Theoretically, there has to be
pinpointing,
a difference if there are
Yeah.
subsequent generations,
Yeah.
but based on abundances or even kinematics, we cannot really define that age to the
Yeah.
precision that we'd like.
Okay, yeah. Thank you.
More questions? Also from Zoom? Questions? I have a couple of them. No one wanted. Thank you, Avrajit. Super interesting and promising. My question is about thorium, because as you have explained very well, it is commonly used in cosmocosmography, but we know it is also a good tracer of the art process production, even better than European. Problem is, of course, the observability. So would you expect any difference in the spread we see in halo stars in thorium to be compared with European, and could it may help to disentangle these different contributions from different, neutron star mergers, supernova, wherever?
Yeah, absolutely. We find a certain groups of stars called the actinide boost stars that show this elevated thorium. And there are certain stars that are lower thorium than what the R process pattern tells us. So these stars are very interesting. We don't know where this actinide boost comes from, and relative abundance of thorium over europium leads us to non-physical ages for these stars. We don't find precise age based on thorium and europium if thorium is elevated or depleted from the expected pattern of thorium. So, but there are theories like one by Hombeck and in 2 years ago, where she suggested that this actinide boost may not require a different R process site. But there are papers that also talk about different sources of R process contributing to thorium. For example, like the lightest R process elements are called limited R because there are sources that has energy, but not sufficient to go to the main R process. They produce the scatter in the lighter R process. Similarly, there are events that produce the heaviest element more than the lighter elements or the main R process elements. That leads to the actinide burst or stars with more thorium than others. But for now, in halo stars, we do find this spread in thorium, but in globular clusters, the spread is very less. But the data is also much less than what we have for halo stars.
Thank you. We also have a question from Zoom. Please go ahead.
Yeah, hi, this is Sivarani. Avrajit, very nice talk, Avrajit. I really enjoyed it. Yeah, and yeah, so I have just two questions. One is on so do you have any plots showing the metallicity difference between R1 and R2 stars? Like, do they show any difference in the metallicity?
I have it, but I don't think I have it on the presentation here.
Do you expect there would be some difference? Because you said the models of neutron star mergers fits the R2 yields, R2 abundances better than R1, right?
Yeah.
From Homburg. So, so just wanted to.
Yeah, we find R2 stars at more metal rich end than the R1 star, but the reason being that for R2 stars, the signals are also stronger, so we can navigate the poor signal to noise in the blue to find signatures at metal rich end. We find R2 stars with at metal reach as -1 or -1.4. But for R1 stars, which are moderately enhanced in R process, are mainly confined to the metal poor end. But when for this study, the RPA5 data that we had, when you look at the metallicity distribution for the R1 and R2, they both peaked at -2.7. So we hardly find any difference between the distributions for R1 and R2 to be different for these stars.
I see. Okay. Interesting. Then the other question is on the globular cluster part. Like you said, the second generation could be polluted by supernovae winds, and so any type of supernovae with whatever masses it would still contribute to alpha enhancement, right?
Yeah.
So you find the second generation to be magnesium poor instead of magnesium rich.
Yeah.
So it cannot be a supernovae wind, right? I suppose.
Yeah, it's primarily AGB winds that pollute that led to the low magnesium, because like at temperatures of 70 megakelvin, the MgL cycle starts operating that converts magnesium to aluminium. And at the same time, the incomplete ON cycle converts oxygen to nitrogen. So when these winds are ejected from the stars during their AGB, they pollute the ISM of the globular cluster that leads to the anticorrelations we find. But in case of supernovae, the simulations tell us that there should be certain supernovae between the formations of the first generations and second generations. But how are the signatures of this supernovae being produced on the, so they lead to the slide, they should lead to a slight increase of the iron peak elements as well as alpha elements, but I believe the time span between these two generations are significantly shorter for the supernovae to really have an impact on increasing the iron levels of the second generation stars.
Okay, so it is primarily AGBs,
Yeah, it's
polluting
primarily,
the.
yeah.
Okay. Yeah, thank you, Avrajit.
Yeah,
nice.
thanks.
Thank you, Professor Sivarani. I think it's time to wrap up. Let's thanks the speaker again. Yeah, thank you.
Thank you.
Okay, thank you also, people from Zoom. We finish here. And again, I recommend you to